Hi all, in this class we can see what is a parallel plate waveguide. So before that we can derive the general solution for waveguide. So first we can see what is a waveguide. Waveguide means one of the early milestone in microwave engineering was the development of waveguide. Waveguide is nothing but it's a medium of transmission for AM wave. So parallel plate waveguide means it is the simplest one that it consists of two conducting sheets separated by a distance. And in this waveguide we can see that this waves that propagate in this transmission line have infinite patterns of electric and magnetic field. These are called modes, and commonly seen modes are TE, TM and TM modes. For a wave propagating in Z direction, TE mode are characterized as we know Z equal to 0, HZ not equal to 0, and TM modes are EZ not equal to 0, HZ equal to 0. And in TM mode we can say that along direction of propagation EZ and HZ equal to 0. So first we will consider the general solution to Maxwell's equation for TE and TM wave propagation, and then apply the solution to specific types of transmission line or waveguide. So first we need to obtain the general solution. After that, using that general solution we can find any waveguides TM or TE mode. So first we can consider a transmission line whose conductors boundaries are parallel to the Z axis and the wave in the line propagate in the positive Z direction. So we can assume that the time harmonic fields with e raised to j omega t dependence, and we can see that the time dependence we can represent using e raised to j omega t. So first we can take the solution of Maxwell's equation to obtain the TE and TM mode components. So first we can write the Maxwell equation. Del cross E is equal to minus j omega mu h. So del cross E equal to minus j omega mu h, and del cross h is equal to j omega epsilon E, so that we can expand the determinant. So we will get del cross E equal to a determinant of h cap, ay cap, az cap, dou by dou h, dou by dou by dou by dou z, ex, ey, ez. So the time dependency we can set dependence dou by dou z. Time dependence we can represent using e raised to j omega t, and the z dependence we can represent using e raised to minus j beta z. That means the wave propagate along plus z direction. So we can find, then we can expand this determinant. We can equate the left and right components. So you will get it as this del cross C. We can expand this determinant, then compare this h we can replace as h x a x cap plus h y a y cap plus h z a z cap. So you will get this del cross C equal to minus j omega mu h as a h cap determinant of expansion is equal to minus j omega mu of x s a h cap plus h y a y cap plus h z a z cap. In that we can compare the unit vectors components. So you will get the first equation is dou by dou y of ez plus j beta ey is equal to minus j omega mu hz. We are representing this dou by dou hz as minus j beta because the dependency e raised to minus j beta z. So if you are finding this dou by dou z, you will get it as e raised to minus j beta z into minus j beta. So the dou by dou z is represented as minus j beta. Then you will get minus dou by dou x of ez minus j beta ex is equal to minus j omega mu hy. Then dou by dou x of ey minus dou by dou y of ex is equal to minus j omega mu hz. So these are the three equations we'll get from this expansion of this determinant. Similarly, we can expand this del cross h is equal to j omega epsilon e. So that also you will get three equations by equating a h cap, a y cap and a z cap. Then we can write this as dou by dou y of hz plus j beta hy is equal to j omega epsilon ex minus dou by dou h of hz minus j beta hs equal to j omega epsilon ey. Dou by dou h of hy minus dou by dou y of hx is equal to j omega epsilon ez. Then we can, using this equation number 1, so this is our equation number 1, and using the equation number 5 you will get what is hs. So you will get the hs component. So you will get this, you can solve this equation number 1, use this equation number 1. Then from this hs we can write hs equal to 1 by minus j omega mu dou by dou y of Ez plus j beta Ey. Then using the equation number 5 we can replace this Ey as this minus dou by dou x of Hz minus j beta Hs by j omega epsilon. Then solving this you will get this Hs in terms of some constant into something into dou by dou y of Ez minus b into dou by dou x of x. You can convert all the equation in terms of Ez and Hz. So you will get this Hs expression. Similarly you can use equation number 2 and 4, then we can find Hy, then and H, then we can find solving 1 and 2 if Hs is eliminated. Then we can see that this Hs, we know what is Hs, then we can get this after eliminating this Hs we will get Ey. So this way we can find all the expressions. So using this equation 1 and 5, first we find what is Hs, then after finding this Hs equation number 2 and using equation number 2 and 4 we found what is Ey. Then from this after finding Hs and Hy 2 and 4, using 2 and 4 we will get what 2 and 4 we will get Hy. So after finding this Hs and Hy we can find Ex and Ey also. So this is the expression, general expression for the components Hs, Hy, Ex and Ey. Then we can define what is TM wave. So TM wave means Ez is not equal to 0 and Hz equal to 0. So in this whole expression we can find that Hs, Hy, Ex, Ey all are in terms of Ez and Hz. So put Hz equal to 0 in this expression, then you will get the TM mode, that is what is Hs, Hy, Ex, Ey while putting Hz equal to 0. So that is TM waves. Then in that we can also replace k square minus beta square term as there, where k square is omega square mu epsilon. So that is we can represent it as kc square. So that is the wave number of material filling the transmission line. Kc is the cutoff wave numbers. Then wave equation we can write this dou square by dou h square plus dou square by dou y square plus dou square by dou z square plus k square into Ez equal to 0, or we can write Ez of xyz is Ez of xy into e raised to minus j beta z. In that dou square by dou z square, already we've said dou by dou z is minus j beta, then dou square by dou z square is minus beta square. So wave equation is dou square by dou h square plus dou square by dou z square, and in this beta square we can write as kc square into e raised to into ezxy equal to 0. So we can using this boundary condition, if while using the boundary condition, then using the boundary condition we can solve this equation 7.1 to 7.4, then you will get the TM mode of respective waveguide. Then we can find what is TE wave. So in that equation, if using this 4 equation replace Ez as 0, then you will get what TE wave. So Ez equal to 0 and Hz not equal to 0, then you will get the 4 components like Hs, Hy, Ex, Ey. Then from that equation we can write dou square by dou h square plus dou square by dou y square plus dou square by dou z square plus k square into Hz equal to 0, or in that this dou square by dou z square is minus beta square. So this k square minus beta square become kc square. So dou square by dou h square plus dou square by dou y square plus kc square into Hz is equal to 0, where Hz is Hz of x comma y e raised to minus j beta z. So to obtain the TE mode expression, we can using the we can use appropriate boundary condition, then solve this equation, then you will get the TE mode of any waveguide. So next we can see how we can solve this equation for parallel plate waveguide. Hi, in this class we can see what is a parallel plate waveguide. So we studied what is a rectangular waveguide. This parallel plate waveguide is the basic waveguide. It is the simplest type of waveguide that can support TM and TE modes. It consists of two flat conducting plates with a material of permittivity epsilon and permeability mu in the region between the plates. So it is a two parallel plates separated by a distance. In between the plates, the medium is having material of permittivity epsilon and permeability mu as field. So first we can see what is the TM mode. So we know in TM mode Ez is not equal to 0 and Hz equal to 0. So that's the condition for TM mode. Ez is not equal to 0 and Hz equal to 0. So for a wave propagating in Z direction, since the parallel plate waveguide doesn't have conducting boundaries along x-axis, we can take dou by dou x of equal to 0. So the wave equation we can write this dou by dou x equal to 0. So if we are considering the wave propagating along Z direction, then the wave equation is dou square by dou y square of Ez x comma y plus kc square Ez x comma y equal to 0. That is the general solution. So we have a second degree equation dou square by dou y square plus k square Ez x comma y equal to 0. So for the general solution for this equation is Z of x comma y equal to a sin kc y plus b cos kc y. So that is the standard general solution for a second degree equation. So we can apply the boundary condition on tangential electric field components. We know that the tangential electric field components are continuous. So we can apply this boundary condition, that is Ez of x comma y equal to 0 at y equal to 0 as well as d. So at y, in this figure we can see that at y equal to 0 and at y equal to d, this electric field component is 0. So we can write at y equal to 0 this Ez of x comma y equal to 0, then y equal to 0 means a sin 0 plus b, you will get it as b equal to 0. Then at y equal to d, you will get 0 is equal to a sin kcd. We already said b is 0, so you will get 0 is equal to a sin kcd in that this equation. Sin sin theta a should not be equal to 0. Then to satisfy this equation, kcd should be equal to n pi. Then only the multiple of n pi, the sin theta is 0. So we can write it as kcd is equal to n pi, or kc is n pi by d, where n is 0, 1, 2, etc. So Ez of x comma y is a sin n pi by dy. So that is Ez of x comma y, or we can write Ez of x comma y comma z as, to represent this propagation also we can include an sin n pi by dy e raised to minus j beta z. So we can apply the solution to equation then equation 7.1 to 7.4. So we have the equation 7.1 to 7.4. This is the general equation for a TM wave. When Z equal to 0 and Hz equal to 0, we will get the general solution. So Hx and Hy, Ex and Ey, you will get it as j omega epsilon by kc square dou by dou y of Ez. Now we know what is Ez, then differentiate with respect to y, that will be Hs. Similarly we can differentiate Ez with respect to x into minus j omega epsilon by kc square is Hy. Then we can differentiate again with respect to x Ez, then into minus j beta by kc square is Ex, and similarly Ey is minus j beta kc square dou by dou y of Ez. So after differentiation, you will get this result as Hs is j omega epsilon by kc an cos n pi y by d e raised to minus j beta z, and Ey is minus j beta k by kc an cos n pi y by d e raised to minus j beta z, Ex and Hy equal to 0. Similarly, we can find what is TE mode. For a parallel waveguide, this TE mode is Ez equal to 0 and Hz not equal to 0. So again we can say that dou by dou x equal to 0 in this in this parallel waveguide. So the reduced wave equation we can write now as dou by dou square by dou y square plus kc square into Hz x comma y equal to 0. So the general solution for Hz x comma y is a sin kcy plus b cos kcy. we can take the boundary condition, that is ex of x comma y equal to 0 at y equal to 0 and d. That means ex equal to 0 at y equal to 0 and d. So you can take this ex representation. So this ex is applying this equation ex equal to 0 at y equal to 0 and d, applying this equation to this ex, that is minus j omega mu by kc square into dou by dou y of hz. You will get ex as what? Ex as minus j omega mu by kc square dou by dou y of hz of x comma y is a sin kcy plus b cos kcy raised to minus j beta z. So after differentiation you will get it as minus j omega mu by kc into a cos kcy minus b sin kcy raised to minus j beta z. So we can now apply the boundary conditions. At y equal to 0 we will get as a equal to 0 and y equal to d means kc into d should be equal to n pi, or kc is n pi by d. So you will get hz of x comma y is bn cos n pi y by d, or hz of x comma y comma z is bn cos n pi y by d raised to minus j beta z. So we can find the remaining component by applying this relation to equation 8.1 to 8.4. So this equation we already derived, hs, hy, ex and ey component. Then you differentiate hz with respect to x and y, then replace respectively. You will get hs, hy and ex. So ex is j omega mu by kc, bn sin n pi y by d raised to minus j beta z. Hy is j beta by kc, bn sin n pi y by d raised to minus j beta z. Ey is equal to h is equal to 0. So this is the Tm and Te mode of parallel plate waveguide.